Hello everybody, and welcome to the continuation of page 60. So in this video we're going to start by filling in this box of definitions here. These definitions are going to relate back to the discussion that we had in example 1. Okay, so let's read this definition together. Let V and W be vector spaces. Let T going from V to W be a linear transformation. Okay, then a function U that takes us from W back to the vector space V is said to be an inverse of T if TU equals something and UT equals something. And what we're going to try to do is to fill in those two blanks. Okay, now one thing before we do that, remember that when you see something like TU, we're really talking about function composition. It looks like multiplication, but what we really mean is T composed with U. And the same is true over here. UT represents U composed with T. We'll kind of keep that in mind as we're going through this. Okay, so to figure out what goes in the blanks there, let's draw a picture here. Okay, so we'll let this circle represent the vector space V, and this circle represent the vector space W. Okay, we'll start with the linear transformation T that's sitting right up here. Okay, it has V as its domain, so you can kind of picture it as starting with the vector little v, and that's going to get mapped over to some vector in W. We'll call it little w. Okay, that's kind of the general behavior of the linear transformation T. And then the function U is the inverse, and so it does the opposite. It's going to start with a vector over in W and map it back to the vector V. Okay, so there's the action of U. Okay, and I'm hoping that with this picture, we can maybe figure out what goes in these two blanks. So let's start with TU. Okay, so again, that's function composition, T composed with U, which means that we're going to apply the function on the right first, the U. Okay, which means that we actually have to start over here with the vector W. We'll first apply the linear transformation U, and then we'll apply the transformation T, which takes us right back where we started. So the net result of TU is to start with a vector W and to end up at that same vector W again. So this is the identity transformation. Okay, we plugged in W, we got out W, and so what we could fill in this blank with is the identity transformation on W. Okay, and then similarly, over here for UT, it's the other way around. We're going to apply the transformation T first, which means that we're going to start over here with the vector little w. We'll apply T first, which takes us to W. Then we'll apply U, which takes us back to the V that we started with. So that's also the identity transformation. Okay, but we start and end in V this time. Okay, so we get the identity map on the vector space V. Okay, good. There's our first sentence. And then moving on with this definition, it says if T has an inverse, then T is said to be invertible. That's just our terminology. And we write T to the -1 to denote the inverse, T inverse. So same notation that you're probably used to with functions. Okay, and we're ready for the second part of our definition. Okay, we say that V is isomorphic. This is a new word. Isomorphic to W if there exists an invertible linear transformation T going from V to W. Okay, now those two words that I underlined, invertible and linear, notice that if we scroll up to the example that we just did, that function T that we came up with had those two properties, linear and invertible. And it turns out that those two properties are what kind of guaranteed this nice correspondence, the fact that we could take an ordered pair AB and kind of identify it with the polynomial A plus BX. Those two objects are analogous to each other. Okay, so going back down to the very last sentence of our definition, such a linear transformation, and what we mean by such is it has these two properties. So linear transformation that's invertible and linear is called an isomorphism. That's our name for the function. Okay, so to kind of summarize this then, okay, if two vector spaces V and W are isomorphic, they may very well be different in the literal sense. Okay, to go back to example 1, ordered pairs and polynomials are not exactly the same thing, but structurally they behave in exactly the same way. That's what we mean when we say isomorphic. The vector spaces are analogous. Okay, so let's make a couple of comments on these definitions that we've made. Okay, so moving on to the next page, we'll fill in some facts about inverses and isomorphisms. Okay, so going down this list, inverses are unique. So given a function, there's only going to be one inverse. Okay, t is invertible if and only if t is both 1-to-1 and onto. You might remember learning that kind of a fact in Intro to Proofs. Number 3, if you take the inverse of the composition of t and u, you actually get u inverse t inverse. The order kind of switches on us. And what would you guess would happen if you took the inverse of an inverse? So t inverse inverse, you're going to get back to just the function t. Okay, and maybe one comment, those first 4 facts that we've listed, those things are true about any function, regardless of whether we're talking about linear transformations or not. Okay, fact number 5, let's see if we can fill this in together. So if t going from v to w is a linear transformation, and v and w are finite dimensional vector spaces of equal dimension, kind of a special situation, then t is invertible if and only if the rank of t equals the dimension of v. Okay, we can actually give a short proof of that. Okay, just kind of referring back to some of the theorems that we talked about earlier. Okay, so starting with the observation that t is invertible if and only if t is both 1-to-1 and onto. Okay, that was fact number 2 that we mentioned up here. And then if you look back at theorem 2.5, t being 1-to-1 and onto under this assumption of equal dimension is actually equivalent to the rank of t being equal to the dimension of v. Okay, so there I'll refer you back to theorem 2.5. You can look at that and confirm that equivalence that we just wrote down. Okay, and then one last fact, this is theorem 2.17 in our textbook. If t is linear and invertible, turns out that the inverse function is also linear. Okay, that's a fact that we're going to feel free to use as we go forward.